Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
What intellectual current carries a mathematician, secure in a tenured professorship at Princeton, to a final, stark declaration that the bedrock of arithmetic is logically flawed? This question animates the intellectual trajectory of Edward Nelson, a figure whose career traces a dramatic arc from foundational orthodoxy to radical skepticism. His life's work presents a fascinating study in the psychology of mathematical inquiry, a journey from building up the most complex structures in theoretical physics to questioning the very axioms upon which all of mathematics rests. To comprehend the final, startling chapters of his intellectual life, one must first appreciate the towering edifice he constructed in his early years. His initial contributions were far from iconoclastic. They were acts of profound consolidation, bringing mathematical rigor to the wild frontiers of physics and cementing his reputation as master craftsman of modern mathematical physics. The middle of the 20th century found physics in a state of triumphant unease. Quantum field theory, particularly the theory of quantum electrodynamics, or QED, was a spectacular success. Its predictions for quantities like the anomalous magnetic moment of the electron agreed with experimental results to an astonishing degree of precision. Yet, behind this empirical victory lay what many practitioners considered a deep mathematical scandal. The very calculations that yielded these brilliant results were riddled with divergent integrals, with infinities that appeared at almost every step. The working solution was a powerful and pragmatic set of techniques known as renormalization. Conceptually, this involved a delicate, almost alchemical procedure subtracting one infinite quantity from another to yield a finite, measurable prediction. Physicists learned how to perform this sleight of hand with remarkable skill, yet a deep sense of dissatisfaction lingered. Paul Dirac, one of quantum theory's principal architects, famously condemned the method, declaring that the theory's fundamental equations were nonsensical. The challenge was clear: to take the wild, successful, and mathematically untamed beast of quantum field theory and place it upon a solid axiomatic foundation. The goal was to construct a theory that satisfied a set of physically reasonable principles, such as consistency with special relativity and the principles of quantum mechanics, from the ground up. Without the ad hoc surgery of renormalization, into this formidable intellectual environment stepped Edward Nelson. His background was in probability theory and functional analysis, fields that, at first glance, seemed quite removed from the high-energy interactions of subatomic particles. His unique perspective, however, would prove to be the key. He initiated a profound shift in thinking by establishing a deep and unexpected correspondence between the world of quantum fields and the world of classical probability. This connection is realized through a mathematical transformation now known as the Euclidean-to-Minkowski continuation. To appreciate this insight, one must consider the stage upon which physics plays out. Physical reality unfolds in Minkowski spacetime, the four-dimensional continuum of special relativity, where three spatial dimensions are interwoven with one time dimension. A key feature of this spacetime is its metric, the rule for measuring distances, which treats time differently from space, a detail responsible for the strange and wonderful effects of relativity. Quantum field theory, in this physical setting, is described by oscillatory, complex-valued mathematical objects whose behavior is notoriously difficult to define in a mathematically sound way. Nelson's revolutionary idea was to perform a formal substitution, a procedure called a Wick rotation. He replaced the real-time variable, let's call it t, with an imaginary time variable, say, I times tau. This seemingly simple change has a dramatic effect. It transforms the geometry of spacetime from Minkowskian to Euclidean, a world of four dimensions, where time behaves like another dimension of space. The immense benefit of this transformation is that the unruly, oscillating expressions of the quantum theory become well-behaved, positive definite expressions in the Euclidean domain. The entire problem is recast from the language of quantum wave mechanics into the familiar and rigorous language of classical statistical mechanics and probability theory. The perplexing infinities of the physical theory, when viewed through this Euclidean lens, become features of stochastic processes akin to the random walks of particles in a fluid, a subject that mathematicians understood deeply. This conceptual bridge was powerful. Nelson formulated a set of axioms, now often called the Nelson axioms, or Euclidean axioms, which were a set of relatively simple conditions that a statistical field theory in this four-dimensional Euclidean space must satisfy. These axioms involved properties like statistical homogeneity and correlation decay over large distances. His central achievement was to prove that if one could construct a theory satisfying the simpler Euclidean axioms, one could then uniquely and rigorously reverse the Wick rotation, analytically continuing the theory back into the physical Minkowski spacetime. The resulting object would be a fully-fledged, relativistic quantum field theory, automatically satisfying the far more complicated and abstract Weightman axioms that had been established as the gold standard for mathematical rigor. He had forged a constructive path, a clear program for building physically realistic models on a sound mathematical footing. This Euclidean approach became an indispensable tool. It forms the conceptual basis for lattice gauge theory, a technique where spacetime is approximated by a discrete grid, allowing for massive computer simulations of phenomena like the strong nuclear force that binds quarks inside protons and neutrons. This work solidified Nelson's place as a mathematician of extraordinary power and insight, one capable of imposing logical order on the most challenging concepts in modern physics. This monumental work on the collective behavior of fields, however, seemed to illuminate a deeper puzzle concerning the behavior of the individual quantum particle, a question that would lead him toward an even more audacious intellectual project. The very architecture of his field theory success seemed to point toward a fundamental question, one that had haunted physics for decades. Having established a method for constructing theories of interacting quantum fields, Nelson turned his attention from the collective to the individual, from the statistical behavior of vast systems to the enigmatic nature of a single quantum particle. The prevailing scientific consensus, the Copenhagen interpretation, offered a spectacularly successful predictive framework. It described a world governed by probabilities, where particles exist in a superposition of states until a measurement forces a definite outcome. This operational prowess, however, came at a steep conceptual price. It required accepting a reality where particles behave as waves and points simultaneously, where the act of observation fundamentally alters the system being observed, and where distant, entangled particles could influence one another instantaneously across vast stretches of space. For many, this felt like an abdication of the physicist's traditional quest for an underlying, objective reality. It was into this philosophical maelstrom that Nelson launched his most ambitious physical theory. He proposed a radical, almost theoretical idea that the strange laws of quantum mechanics were themselves an emergent phenomenon, a statistical shadow cast by a deeper, entirely classical reality. This program, which he christened Stochastic Mechanics, sought to derive the entirety of quantum behavior from the familiar principles of Newtonian physics and probability theory. The central premise is one of deceptive simplicity. Imagine a single classical particle, a tiny point-like object, moving through a pervasive, unseen medium. This medium subjects the particle to relentless, random buffeting, a universal Brownian motion. The particle's trajectory is therefore a chaotic, jittery dance, a diffusion process governed by random fluctuations at an infinitesimal scale. Nelson's genius was to demonstrate with unimpeachable mathematical rigor that the statistical mechanics of this classical diffusion process are described precisely by the Schrödinger equation. This equation, the very cornerstone of quantum mechanics, dictates the evolution of the quantum wave function. In the standard view, the wave function represents the complete state of a quantum system, its value at any point in space related to the probability of finding the particle there. Nelson's work offered a profound reinterpretation. The wave function became a derived quantity, a mathematical tool for tracking the statistical properties of a real, classical particle undergoing a random walk. The probabilistic nature of quantum mechanics was demystified. It was the same kind of probability one finds in the thermal motion of gas molecules, elevated to a universal principle. The derivation itself is a masterpiece of physical and mathematical reasoning. In a classical diffusion process, a particle's motion is characterized by two distinct velocities: a forward drift velocity, representing its average future motion, and a backward drift velocity, reflecting its average past motion. For a simple random walk, these are equal and opposite. Nelson introduced the concept of an osmotic velocity, representing the tendency of the particle to diffuse away from regions of high concentration, and a current velocity, representing the overall flow. He then postulated that the particle's acceleration, governed by Newton's second law, F equals ma, was determined by the mean of the forward and backward time derivatives of its velocity. When these kinetic definitions were combined within a variational principle of least action, the resulting dynamical equation for the particle's probability density could be transformed through a clever change of variables, combining the two real-valued velocity fields into a single complex-valued field. The equations of motion for this classical stochastic process coalesced into the familiar form of the Schrödinger equation. The quantum weirdness appeared to dissolve into classical statistics. To place this audacious idea on a firm mathematical foundation, Nelson reached for one of the most powerful and esoteric tools of modern logic, Abraham Robinson's nonstandard analysis. The standard calculus deals with infinitesimals through the machinery of limits, a process that avoids confronting the idea of an infinitely small quantity directly. Nonstandard analysis, by contrast, provides a rigorous framework that includes actual infinitesimal and infinite numbers. This was a perfect language for describing the continuous time Brownian motion at the heart of stochastic mechanics. It allowed Nelson to treat the infinitesimal time steps and random kicks of the diffusion process with complete mathematical precision, building his derivation on a bedrock of logical consistency. For a time, the program showed extraordinary promise. It reproduced a wide range of quantum phenomena from a purely classical starting point, offering an intuitive, realist picture that the Copenhagen interpretation lacked. It provided a clear physical mechanism for the uncertainty principle, which emerged as a direct consequence of the underlying diffusion. A particle's position and momentum could have definite values simultaneously, but the random background fluctuations would make it impossible to measure both with arbitrary precision. Yet, the deep strangeness of the quantum world resisted being fully tamed. Stochastic mechanics encountered significant hurdles, explaining particle spin and intrinsic angular momentum with discrete, quantized values and no clear classical analog proved exceptionally difficult. Furthermore, the theory struggled to reconcile itself with the implications of Bell's theorem, which demonstrated that any local, realist theory of the type Nelson proposed would be inconsistent with the experimentally verified predictions of quantum mechanics. While modifications and extensions were proposed, they often required fine-tuning or assumptions that compromised the original theory's classical elegance. Despite these challenges, the intellectual legacy of stochastic mechanics is immense. It stands as perhaps the most serious and mathematically sophisticated attempt to derive quantum physics from classical principles. It forced a generation of physicists and mathematicians to re-examine the relationship between classical and quantum probability, stimulating a rich field of research that continues to this day. The theory remains a vital reference point in the ongoing debate about the meaning of quantum mechanics, a powerful testament to the idea that even our most successful scientific theories may be provisional descriptions of a still deeper reality. Nelson's profound engagement with the foundations of physical law, his quest to ground the probabilistic world of the quantum in the deterministic world of Newton, would ultimately lead him to question the very foundations of the language he was using. His intellectual journey was about to take another, even more radical turn, away from the nature of physical reality and toward the nature of mathematical truth itself. This profound reorientation of intellectual energy would lead Nelson into the very bedrock of certainty, the realm of pure number. His investigations into the probabilistic heart of physics had revealed the immense power of mathematical structures to describe the world. Yet, this very power raised a deeper, more unsettling question for him. What was the ultimate source of mathematical truth? On what foundation did the entire edifice of logic and number theory rest? This inquiry would consume the latter part of his career, culminating in a challenge so audacious, so fundamental, that it aimed at the very heart of mathematics, the consistency of arithmetic itself. The intellectual landscape Nelson began to survey was dominated by a philosophy inherited from the 19th century, a perspective that had become so ingrained it was almost invisible. This was the classical view, championed by figures like Georg Cantor and David Hilbert, which accepted the existence of what are called completed infinities. The entire set of natural numbers, 1, 2, 3, and so on, extending forever, was treated as a single, finished, existing object. Mathematicians could speak to this set, the set of all real numbers, and other infinite collections, as if they were things one could hold and manipulate. This conceptual leap while enormously fruitful, rested on a foundation of faith. It relied on logical principles, such as the law of the excluded middle, which asserts that any proposition is either true or false, even if we have no way of ever determining which. This allows for what are known as non-constructive proofs, arguments that prove something exists without ever providing a method to find it. For Nelson, this was a profound source of intellectual discomfort. His instincts, honed by a career spent grounding abstract ideas in physical or probabilistic reality, recoiled from this level of pure abstraction. The problem became vivid when considering numbers of unimaginable scale. He would often use the example of a tower of powers, such as 2 raised to the power of 2, which is then itself raised to the power of 2, 1,000 times over. Classical arithmetic asserts that such a number is either prime or composite. The law of the excluded middle guarantees this. Yet, this number is so colossal that it could never be written down in our universe, its digits far exceeding the number of particles in the observable cosmos. To Nelson, a statement whose truth or falsity is forever beyond any possible human or mechanical verification began to seem less like a mathematical fact and more like a metaphysical speculation. He felt that mathematics had become detached from its moorings in what is concretely knowable or computable. His response was to embrace a philosophy of radical constructivism, a position often termed ultrafinitism. This viewpoint is even more stringent than the intuitionism of L.E.J. Brouwer, which, while rejecting the law of the excluded middle, still countenanced potentially infinite processes. Nelson's vision of mathematics was far more austere. He sought to rebuild a portion of mathematics from the ground up, using a system that admitted only those objects and proofs that were, in principle, feasible. The meaningfulness of a mathematical statement was tied directly to the possibility of its verification. The central task, as he saw it, was to formalize this deep-seated philosophical skepticism. It required creating a new system of logic, one that was predicted in nature, meaning it disallowed the formation of sets or objects that referred to a totality of which they themselves were members. This was a way of preventing the self-referential loops that can lead to paradox and, in his view, to assertions about inaccessible infinities. This project was a monumental undertaking. It involved crafting a formal theory with its own axioms and rules of inference, a system designed to mirror the workings of a finite human mind. This system was inherently weaker than the standard logical frameworks used by most mathematicians. It was a world without the comforting certainty of the law of the excluded middle, a world where infinity was a process of endless succession, never a completed object. Within this carefully circumscribed intellectual laboratory, Nelson began to re-examine the foundational theory of arithmetic that every mathematician learns. Peano Arithmetic, named for the Italian mathematician Giuseppe Peano, this set of axioms provides the formal basis for the properties of the natural numbers. It is the system that formalizes our intuition that every number has a successor, that induction works, and that basic operations like addition and multiplication behave as we expect. For nearly a century, the consistency of Peano Arithmetic had been an article of faith for working mathematicians. While Gödel's incompleteness theorems had shown that Peano Arithmetic could never prove its own consistency, the belief was that the system was, in fact, free of contradictions. It was considered the securest part of the entire mathematical enterprise. It was precisely this citadel that Nelson set out to assail. From within his own, more restrictive finitistic system, he developed a long and highly technical argument. His unique approach was to formalize the very notion of computability and then to analyze the behavior of certain types of polynomial time functions. He explored how these functions, which are considered computationally feasible, would behave under the assumptions of standard Peano arithmetic. His line of reasoning, pursued with meticulous detail through the machinery of his predictive logic, led him to a conclusion that sent shockwaves through the mathematical community when he announced in 2010. He claimed to have constructed a formal proof that Peano arithmetic was logically inconsistent. This was a declaration of breathtaking consequence. An inconsistency in Peano arithmetic would mean that one could, following its rules, prove both a statement and its opposite. For example, one could prove that 2 plus 2 equals 4 and also that 2 plus 2 equals 5. If true, the entire structure of number theory, and by extension vast areas of modern mathematics that rely upon it, would crumble. Nelson's claim was a direct technical assault on the coherence of mainstream mathematics. It was one thing to harbor philosophical doubts about infinity. It was another thing entirely to present a paper filled with formal logical deductions purporting to have found a fatal flaw in the universally accepted language of number. His intellectual journey, which began with a subtle interplay of particles and probabilities, had led him to stand before the entire edifice of mathematics and declare that its very foundation was unsound. The mathematical world received this stunning proposition with a mixture of profound skepticism and urgent curiosity. A claim of this magnitude, delivered by a scholar of Nelson's stature, demanded immediate and rigorous scrutiny. The community of logicians, in a remarkable display of collaborative, rapid response peer review conducted largely through online forums and blogs, descended upon the preprint. The analysis that followed was surgical, deep, and ultimately definitive. What emerged from this intense period of examination was a multi-layered resolution. On a technical level, mathematicians like Terence Tao and others identified specific points in the argument where the deductive steps appeared to falter. These were subtle, highly specialized issues within the formal logic, yet they were sufficient to break the chain of inference required for the proof to hold. The more profound insight, however, went to the very heart of Nelson's philosophical project. The core issue lay in the logical framework he employed. His proof was constructed within his idiosyncratic system of predicative finitism, a system deliberately weaker than the standard logic used by most mathematicians. He had forbidden himself the use of certain powerful tools of reasoning, particularly those related to the full force of mathematical induction on complex formulas, which he believed harbored the seeds of contradiction. Therefore, even had his proof been technically flawless, it would have demonstrated something quite specific, that Peano arithmetic is inconsistent asterisk when viewed through the lens of his restricted finitistic logic asterisk. This is a fascinating result of the philosophy of mathematics. Yet it is a different proposition from finding a contradiction within Peano arithmetic using the accepted, powerful axioms of Zermelo-Fraenkel set theory, the bedrock of modern mathematics. The grand edifice had withstood the assault. The inconsistency was an artifact of the tools used to probe it, a reflection in a carefully constructed mirror rather than a crack in the foundation itself. For the working mathematician, the crisis was averted. For Edward Nelson, it was a culmination of his intellectual arc, a final, powerful statement of his deep-seated conviction that the abstractions of his field had outrun their grounding in tangible reality. This final, audacious chapter of his career provides the key to understanding the whole. Looking back across the landscape of his contributions from the rigorous constructions in quantum field theory, to the physical intuition of stochastic mechanics, to the radical finitism of his later years, a powerful, unifying theme becomes clear. Each intellectual pursuit, in its own way, was a quest for embodiment, an attempt to anchor the soaring, abstract creations of the human mind to something more solid, more intuitive, more physically or computationally real. His early work in constructive quantum field theory can be seen in this light. The problem of the 1960s was one of rampant, successful, yet mathematically unsound formalisms. Physicists possessed a set of rules that gave stunningly accurate predictions, but the mathematical objects they manipulated, like interacting quantum fields, were ill-defined. Nelson's contribution was to take these ethereal concepts and give them a solid footing in the rigorous world of probability theory and functional analysis. He was building a bridge from the physicists' brilliant intuition to the mathematicians' demand for logical coherence. He wanted the abstract language of fields to correspond to something concrete, well-defined random processes. His development of stochastic mechanics was a more direct expression of this same impulse. Here, he confronted the central mystery of quantum mechanics, the wave function, and its probabilistic interpretation. The standard Copenhagen interpretation asks us to accept this abstract mathematical object as a complete description of reality, with all its attendant paradoxes of measurement and collapse. Nelson's approach was a radical counterproposal. He asked, what if the quantum world is the result of a deeper, classical, and more intuitive physical process? What if each particle is performing a simple random walk, a diffusion process governed by classical mechanics, and the Schrödinger equation is merely the statistical description of that underlying motion? He sought to replace the abstract, ghostly wave function with a tangible image of a particle being buffeted by an unseen background field. The theory ultimately fell short of its grand ambition, yet the motivation behind it is crystal clear. To demystify the quantum, to ground its strange mathematics in a process one could almost visualize. His final turn toward ultrafinitism was a philosophical endpoint of this lifelong journey. Having sought to ground physics in tangible processes, he turned his attention to the very foundations of the language used to describe those processes, mathematics itself. He came to believe that the concept of the completed infinite set, the cornerstone of modern set theory, was a fiction. For Nelson, a mathematical object could only be said to exist if it could, in principle, be constructed or specified by a finite computational process. The set of all natural numbers, stretching out to an infinity that can never be reached, was for him a step too far into abstraction. His challenge to Peano Arithmetic was the ultimate expression of this belief. He was asserting that the moment our mathematical language speaks of these infinite totalities, it loses its coherence and falls into contradiction. His quest for embodiment had led him to the most fundamental ground of all the finite, computational capacity of the human mind itself. The threads connect from the random fields of CQFT to the diffusing particles of stochastic mechanics to the finite computations of his logical program. Edward Nelson was consistently engaged in a single, magnificent project. He was pushing back against the 20th century's embrace of pure abstraction, perpetually seeking to remind his colleagues that mathematics and physics are, at their best, sciences rooted in the comprehensible. His life and work, therefore, offer a profound lesson. He was a brilliant Socratic gadfly for the modern mathematical sciences. Like the ancient philosopher who wandered Athens asking uncomfortable questions, Nelson prodded the comfortable consensus of his fields, forcing them to re-examine their most deeply held assumptions. His specific answers, whether in stochastic mechanics or the foundations of arithmetic, were ultimately set aside by the community. Yet, the enduring value of the gadfly lies in the sting, in the productive discomfort that compels a deeper self-awareness. He forced physicists to ask what, precisely, their equations correspond to in reality. He forced mathematicians to confront the philosophical choices embedded within their axioms. His career is a testament to the power of intellectual courage, the willingness to follow a line of reasoning to its most radical and unpopular conclusions. He reminds us that even in the most abstract of disciplines, the questions we choose to ignore can be as important as the ones we choose to answer. Edward Nelson's legacy is the persistent echo of his profound and challenging inquiries, a permanent intellectual summons for mathematics and physics to perpetually re-examine the very ground upon which their magnificent structures are built.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.